Welcome back to Abstract Algebra. Today, what we're going to do is talk about quotient groups and normal subgroups. So remember that we're trying to classify all groups up to isomorphism, and we would like to be able to create new types of groups out of old groups. And very common construction in mathematics to create new groups is that of a quotient group. I have a group, I have another group, and I'm going to do a quotient to create some other new type of group. So how is that going to work in here? Let G be a group, and let H be a subgroup. Then what I would like to is to construct a new group that we're going to call G mod H, or the quotient of G by H. And what is that going to be? That is equivalence classes. We're going to say that G and G prime are equivalent modulo H if and only if, well, usually what we do is G prime minus G is in H. So in this case, we have a multiplication. So G inverse, G prime G inverse is in H, which means that G prime is G times H for some H in H. And what that means is that the equivalence class of G is actually the coset GH. So this is, in fact, the elements are going to be cosets, left cosets of H in G. So this is the set of left cosets of H in G. And what I would like to do is to make this into a group. Okay, so let's see how, if this works. If this is going to be a group, what is the operation with a binary operation defined by what? Well, if I have this coset and I want to multiply it by this coset, then there is only one sensible way of doing this. I hope that this is a binary operation, which is the coset generated by G1 and G2. So is this an operation? Is this a valid binary operation? Well, we're going to see in a moment that no, in general, it is not. So let's see. Is that star well defined? So remember, we are doing G1H, that coset, times this coset. I want it to be this new coset. But the problem with cosets is that they have more than one generator. So let's just, to remember what cosets are, let's look at Z modulo 6 and let H be the coset, or the subgroup rather, generated by 3. So that is a subgroup. And what are the cosets? Well, remember that I have 0 plus H. That will be just 0, 3. So that is just H. But that is the same, exact same as 3 plus H. So you see now that H has two generators, 0 and 3. What about 1 plus H? This is the coset 1, 4. But that is exactly the same as the coset generated by 4, because 4 plus 0 is 4, 4 plus 3 is 7, which modulo 6 is 1. So I get the same thing, and 2 plus H is 2 and 5, but that is the same as 5 plus H. So the cosets, Z modulo 6, Z modulo Z 0, 3, the set of cosets is going to be 0 plus H, 1 plus H, and 2 plus H. But the problem is that they all have other names. I could also have said this is 3 plus H, that this is 4 plus H, and this is 5 plus H. So whatever operation I define over here, it should not depend on the generator I'm giving to my coset, because there is no reason for me to choose 3 over 0 or 4 over 1. So it has to work for both generators. And does it really work in general? It doesn't. So in here, in this example, it does work. So for example, suppose I want to add 1 plus age, and I want to add it. This is the addition I'm defining on cosets. I want to add it to 2 plus age. That should be the addition of the 1 plus 2 plus age. So that should be 3 plus age, which remember is just age. And what happens if I choose another different generator? Age, this 1 plus h also has generator 4, and 2 plus h also has a generator 5. That would give me 4 plus 5 plus age. 4 plus 5 is 9 plus age, but 9 modulo 6 is 3 plus age, which is also age. So it does work in this case. Works in this case. But what about in general? But in general, suppose that I have G1H coset, and suppose that that is the same coset as G1 prime H, and that we have G2H, and that is the same coset as G2 prime H. Does this imply in general that G1H star G2H is the same as G1 prime H star G2 prime H? Well, let's see what this is. This is, on the left-hand side, I have G1, G2H, and on the right-hand side, I have G1 prime, G2 prime H. Now, are these two things the same? Well, we do have that G1 prime. Because of this relationship here, I know something about G1 prime and about G2 prime. Well, G1 prime has to be in this coset. So this implies that G1 prime has to be G1 times something in H for some H1 in H. And similarly, G2 prime has to be G2 H2 for some H2 in H. So this side is G1 H1 G2 H2H. Now, H2 times H, anything in H times something in H is in H, so this is just H. So this is just G1 H1 G2H. But now what I would like is that this is, well, what I would like is to be able to switch H1 and G2. But in order to do that, because if I am able to switch, then this H1 and H will just be capital H, and it would work. Okay, but in here, what's happened is that I would need that H1 G2 is the same as G2 H. I don't need it to be exactly H1. Actually, it could be something like H3. Okay, something like this. If that happened, this would work. But this equality does not always need to happen. That H1 G2 is G2 times something in H is not completely necessary. And this has to happen for all H1s in H and for all G2 in G. So what actually would need to happen is that age G2 is the same as G2H. That's what would need to happen. For this to happen for all H1s and all G2s. For this to happen, we would have to have that the left coset is the same as the right coset. And that is not always the case. So let me give you an example where this does not happen. So is it always the case that GH is the same as HG? And the answer is no. And for example, if you take G to be S3, and H is going to be the subgroup generated by the permutation 1, 2, which is just the identity and 1, 2. This subgroup, if I try to do, let's look at 1, 2, 3H. Okay, then 1, 2, 3H is going to be, well, that coset is going to be 1, 2, 3, and 1, 2, 3 times 1, 2. What is this? This permutation is 1 goes to 2 and 2 goes to 3, so 1 goes to 3. 2 goes to 1 and 1 goes to 2, so 2 is fixed, and 3 goes to 1, so it's this one. So this coset is just 1, 2, 3, and 1, 3. But what is H times 1, 2, 3? That is, well, it would be 1, 2, 3 again. I'm multiplying this by 1, 2, 3 on the right. So now I get 1, 2 times 1, 2, 3. But this permutation is 1 goes to 2 and 2 goes to 1. So 1 is fixed. Then 2 goes to 3. And 3 goes to 1 and 1 goes to 2. So 2 goes to 3. So this coset is 1, 2, 3, and 2, 3, which is not the same as we got above. So we get that 1, 2, 3H is not H times 1, 2, 3. So using for this G for S3, trying to do the quotient by this subgroup H would not work. And I would not have a multiplication, a well-defined multiplication of cosets of H. Okay, so we are going to call subgroups normal if this does happen. So let me write a definition. A subgroup N for normal is a subgroup N of a group G is said to be normal. That's what we're defining here. If the following happens, that Gn is the same as Ng for all G in G. If so, we write that N, let me just write the word right correctly. We write N with this symbol, with this triangular symbol, that N is normal in G. So let me give you an example. First of all, if G is an abelian group and H is any subgroup, then H is normal in G. Why? Because take H, take any coset, so let G be in G, and take a left coset. Remember, this is all the elements G times H for G in G. But because it is abelian, this is the same as every element of H times G as we run. I'm sorry, this is not, this is, oops, as we run elements in H. we fix G, and then we multiply that G by every element in H. Now, because it is a billion, every G times H is H times G, as H runs over elements in H, and that is H times G. So every subgroup of an abelian group is normal. So for example, we had 0, 3 inside Z mod 6 is normal, and that's why we are going to be able to do a quotient of Z modulo 6 modulo this other subgroup to get a quotient. However, in S3, there are subgroups that are normal. This is going to be my G. There are subgroups that are normal and subgroups that are not normal. So let's see what happens. So we've seen that, well, for example, the identity is a subgroup. And if I take that to be H, G times the identity, that is just G times identity. So it's just this one coset. And that is the same as the identity times G. So that is normal. Great. The identity subgroup is always normal in the entire group. S3 as a subgroup of S3, that is definitely a subgroup, and it is also normal because G times S3 is just going to be left multiplication of S3, which is a bijection. We saw that before, and that gives me all of S3 back, which is the same as multiplying on the right-hand side. So that implies that S3, the entire group is normal in the group. Those are normal subgroups. Great. Now, when we looked at the subgroup generated by 1, 2, we saw that that there is already one element that doesn't work, and that 1, 2, 3H is not H times 1, 2, 3. And if you want to prove if a subgroup is normal, you have to prove it for every G. But if you want to prove that a subgroup is not normal, it's enough to find one G where it doesn't work. So that tells me that H is not normal in G. Okay. What about H 1, 2, 3? What about the subgroup generated by 1, 2, 3? That's a subgroup of order 3 in S3. Let's see if that is normal. This subgroup is the identity 1, 2, 3, and 1, 2, 3 times 1, 2, 3 is 1, 3, 2. So what happens if I do 1, 2, H? What I get is 1, 2, and then 1, 2 times 1, 2, 3, and 1, 2 times 1, 3, 2. And if you do all those computations, what you get is 1, 2, 2, 3, and 1, 3. Okay. And if I do H times 1, 2, then what I'm going to get is 1, 2, and 1, 2, 3 times 1, 2, and 1, 3, 2 times 1, 2. And you can do the computations and see that actually what I get is 1, 2, 1, 3, and 2, 3, which is the same. So that works for that one. Let's see. Okay, so that works. That's nice. Is it going to work for everything? You can verify that 2, 3 times H. Remember, H here is the subgroup generated by 1, 2, 3. 2, 3, it is also that, and 1, 3 times H, it is also that. What happens if I do 1, 2, 3 times H? Well, 1, 2, 3 is in the set H, so this is actually just H, so it will be the same as H 1, 2, 3 on the right. And if I multiply by 1, 3, 2 H, I will get H, and I will get the same as if I multiply on the right. So with all the work we had above and this work, what we've proved is that this age is actually normal in S3. So the subgroup generated by 1, 2, 3 is normal. So S3 has subgroups that are normal and subgroups that are not normal. So sometimes they work, sometimes they don't work as normal subgroups. Then let me now go back to the issue of a quotient group and prove the following theorem. Let n be a normal subgroup of G, then G modulo n, the set of cosets uh, with respect to the operation Gn star G prime n is G prime n is a group with Gn elements where, remember that Gn is the index of n in G, and recall that what that is the number such that, remember that G can be partitioned. There is a number of cosets, 1 through some n, such that those cosets are, they partition G. So there will be some number of cosets. Um, um, so this is, if G is finite, this n will be finite. If G is, if this index is infinite, then this index is infinite. But if it is finite, then it is the number of the finite number of cosets that cover all of G. Okay, so that is the index. And the index is because it is the number of the different cosets, will be the number of elements of the quotient. So let's prove that this is actually a group. So here's the proof. First of all, the number of elements in here is the number of elements in here. So it is the number of cosets, but it will be the number of distinct cosets, the number of distinct cosets of n, left cosets in this case, and that is precisely the index. Now, we want to prove that this is we want to prove that this is a group. So first, we're going to prove that this multiplication is well defined. And to prove that it's well defined, suppose I have a coset that is the same, is given. The only problem with the well-definedness is that there might be more than one representative for the coset. And I have another coset, and those are represented by different representatives, B and B prime, A and A prime. And now let's see how much is A and how much is an times bn should be the same as a prime n times b prime n. This is just abn by the definition, and this is going to be a prime b prime n. Now, from these, we realize that this says that a prime has to be a times some n1, and b prime has to be some b times n2 for some n1 and n2 in n. Then I can rewrite a prime b prime as a1 n1 b and n2. So a times n1 and b times n2n. Now, n2 times n is the same coset n because n2 is in n. So this is a n1 b n. Now, we assume that n is normal in G, which remember that means that Gn is the same as Ng for all G in G. So B times N is the same as N times B. So this is A and 1 N times B. Now, this is because N is normal in G, I can switch left coset by a right coset. N1 times N, N little n1 is in N, so this is the same as A and B. And now I can do the flip again. This is the same as, so this is what I was trying to see if they're the same, and A times NB is the same as ABN. And therefore, we have reached that this is the same as this, and therefore the multiplication is well defined. Great. So that is the first step. The multiplication of my group is well defined. What other properties do we need? We need associativity. Is multiplication associative? So I'm going to do an times bn times cn, and I want to show that that is the same as if I move the parentheses around. But this an times bn, or the inside the parentheses, this is an times bcn, and that is again the way the multiplication works. This is abc times n, but now g is associative. The multiplication on G is an associative operation. So inside this parenthesis here, the operation is happening in G, which I already know is a group. So this is the same as AB times C times N, and that is ABN times Cn with a new operation. We're putting on cosets, and this will be the same as AN times Bn times Cn, which is what I wanted to check. So therefore, the multiplication is associative. Great. Do we have an identity element for this operation? Yes, it turns out that the identity will be the identity. So the new identity will be the identity times the subgroup n, which is in fact just the subgroup n. So that is that coset will work as an identity because an times en is ae times n, but these little identity that is the identity in G. Okay, this one here, this is the new identity we're trying to define in the quotient, but the little e that is multiplying n is the identity in G, and well, that works as the identity in G, so that is just an, and if I multiply on the right, I also get EAN, which is also just AN. So it works as an identity element. And finally, do we have inverses? So now, what is going to be if I have one coset, what is going to be the inverse coset is going to be, we're going to define it to be G inverse times n. So the coset, the inverse of the coset Gn will be the coset generated by G inverse. Because let's see that it works. If I multiply Gn times G inverse n, then what I get is G inverse, and which is En, which is the identity I defined, that I checked that it's going to be an identity element for the quotient group. And similarly, G inverse times Gn I do get G inverse G times n, which is identity times n, which is n, which is identity. So it is a group. Thus, these this is a group, which is what I wanted to show. And notice, though, remark that G mod n does not need to be abelian. G1n times G2n will be G1 G2n, and in general that is not G2 G1n, which would be G2n times G1n. So this is not necessarily the case. And what it does tell me, though, is that what we do get that if G is abelian, and H is any subgroup, then G modulo n is an abelian group. And the proof of this is that if G is abelian, implies that n is normal automatically, and G mod n will be also abelian, because the multiplication G1 G2n is the same as G2 G1n, and this would be the multiplication of two cosets, and this is the multiplication of the two cosets in the opposite order. So you do get abelian. This is for all. This is for all G1, G2 in G, and therefore we get that the quotient of an abelian group is always another abelian group. Okay, so in the next video, I'm going to prove some properties of normal subgroups, and also I will give some examples of normal subgroups and their quotients in more detail.